Welcome to Generative AI Futures podcast series. Today we're doing a deep dive into the Google Coral NPU. Our mission really is to get under the hood of this full stack open source platform. It's designed for what feels like the next big jump in computing, bringing powerful, genuinely always on AI to, well, tiny edge devices, wearables, basically.
Yeah, and the context here is just crucial, isn't it? For, the last 5 years or so, AI meant huge models, massive data centers, cloud stuff.
Right.
But if AI is going to be truly assistive, real-time, understanding your context, almost invisible, it absolutely has to run right where the data happens on your device.
Interesting, it's dealing with really tight constraints.
Exactly. Devices constrained by tiny batteries.
Yeah.
Think your watch, maybe smart glasses down the line. That's the challenge.
And that whole shift, moving from the cloud essentially onto your wrist,
Right.
that's where our sources pinpoint three major hurdles. They call them the critical crises for edge AI. First one, the performance gap. It's pretty straightforward. The complex models we actually want to run, especially these newer transformer types, they just need huge amounts of compute power. They'd instantly overwhelm the power budget, the heat limits of a small battery device.
Absolutely. You just can't shrink a server chip and expect it to work.
Yeah.
And that leads straight into the second crisis, something developers know all too well.
Huh.
The fragmentation tax.
Ah, yes.
The current edge world, it's a maze, loads of different proprietary processors. Each one needs its own special, expensive, time-consuming optimization just to get an ML model compiled and running efficiently.
Makes scaling a nightmare, I imagine.
Totally. And the third piece, something we talk about a lot, is the user trust deficit.
Right. Privacy.
Yeah. If an AI is going to be truly personal, it needs access to really sensitive data, your movements, conversations, environment. So to earn that access, the platform itself has to basically guarantee privacy and security.
Okay, so Coral NPU is positioned as Google's shot at providing like one single open standard answer to tackle all three of those problems at once: performance, fragmentation, and trust.
And it really starts with the architecture.
Yeah.
What's quite interesting here is how Coral NPU flips the usual chip design script. Normally you start with a standard CPU core, right? And then maybe you bolt on some accelerators later, almost like an add-on. Coral NPU goes AI first. It prioritizes the machine learning engine, the big matrix math part that the neural networks rely on right from the get-go, built from the silicon up for efficient on-device AI inference.
That makes a lot of sense. It avoids that old trade-off. General CPUs are flexible, but power hogs for ML, and pure accelerators are efficient, but inflexible for everything else. So Coral NPU tries to find that sweet spot, building its reference design on the open RISC-V standard.
Exactly. And if you break down the core components, the building blocks, they're quite logically divided. First, you have the scalar core. Think of this as a lightweight, C-programmable processor. Its main job is like traffic control, managing data flow, system tasks, the usual CPU stuff, RV32I compliant.
Okay, the coordinator. Then you get to the heavy hitters.
Right. You've got the vector execution unit. This is where the parallel processing happens. It's a SIMD coprocessor, single instruction, multiple data. Basically, it can crunch through array operations, activation functions, lots of things simultaneously. It's built on the RISC-V vector standard, RVV 1.0, with these wide 256-bit vector registers, handles general ML compute very efficiently.
And the main event.
And then the core accelerator, the powerhouse, the matrix execution unit. This is purely for matrix multiply accumulate operations, or MATMUL. That's the absolute bedrock math for neural networks. The sources mention this outer product engine design capable of, get this, 256 MASI operations per clock cycle. That density is how they aim to squeeze so much performance from such a tiny power budget. Though, fair note, sources say this part is still under active development or evaluation.
And technically, how does it all connect?
Yeah. It's designed as an AXI4 or tiling peripheral within a larger system on chip.
Okay.
It uses the AXI4 standard, that's the advanced microcontroller bus architecture, to talk to the rest of the system. Handles addresses, handshakes, data bursts. And it implements standard RISC-V control and status registers, the CSRs, for configuration and control.
Okay, let's talk about that power budget again. That 10 milliwatt figure really jumps out. The performance target is around a 512 giga operations per second, 512 GOPS, but 10 milliwatts. What does that actually mean for a user?
Well, it's kind of revolutionary for battery life. Think about your phone. Even with the screen off, the main processor might still be sipping hundreds of milliwatts just idling. 10 milliwatts. That's roughly the power draw of a single, very low power LED. It's minuscule, and that efficiency is the key to making AI always on. It's the difference between a device maybe checking your context every few minutes versus one running complex AI constantly all day without killing the battery.
Okay, so that's the metric that enables truly ambient computing. Very cool. So the hardware is clearly optimized for ultra-low power. Let's switch gears to the software stack, because this is crucial for tackling that fragmentation tax you mentioned earlier. Amazing hardware isn't much use if developers can't program it easily.
Exactly. And this is where the open source software stack, I think, really becomes the potential game changer. The core problem is, how do you take a model built in, say, TensorFlow or PyTorch, and make sure it runs optimally on this specialized 10 milliwatt chip? And importantly, runs well, regardless of who actually manufactures the final silicon based on this reference design.
Right, the consistency problem.
The solution is this quite sophisticated compiler toolkit. You could think of it maybe as a construction manager for the machine learning model.
Okay, and the sources call out two key pieces working together here. First is MLIR, multi-level intermediate representation.
Right. MLIR is like the foundational framework. It's modular, it's flexible, designed for representing code at different levels of abstraction. It's built for handling complex, heterogeneous systems like this.
And built on top of MLIR is IRE.
Correct. IRE, the Intermediate Representation Execution Environment. That's the actual compiler and runtime system. It takes the ML model, uses MLIR's infrastructure, and lowers it, meaning it translates it step by step into a unified intermediate format that's super efficient for the target hardware. And they've really focused on efficiency. IRE aims for final binary sizes that could be as small as like 30 kilobytes on embedded systems. Very low overhead.
Let's walk through that process, the compilation workflow. It sounds like they've tried to make it smooth for developers. Step one is just bringing in your model, right? Import model.
Yep. Start with your trained model from TensorFlow, JAX, PyTorch, whatever you're using. Step two is conversion. The model gets converted pretty quickly into a standardized format. The sources mention the stable HLO dialect.
Stable HLO.
Think of it as a universal language, a common blueprint for ML models. Doesn't matter which high-level framework you started with, stable HLO provides a consistent definition. This is key to solving that fragmentation problem. Everyone targets this common format first.
Okay, so the compiler gets this universal blueprint. Then step three, progressive lowering. What's that?
So this is where the IRE compiler really does its magic. It uses a hardware-specific backend or plugin that knows all about the Coral NPU architecture, the vector unit, the matrix unit capabilities. And it systematically translates or lowers that stable HLO representation through potentially several intermediate stages or dialects, getting closer and closer to the actual machine instructions the NPU understands.
Optimizing at each step.
Exactly. That progressive part ensures you end up with highly optimized machine code tailored for the NPU.
Which leads to step four, deployment. You get a final, compact binary file ready to run on the edge device. Now, the sources also mention a lot about simulation and verification tools. Why spend so much effort there if you're using standard stuff like RISC-V?
Well, because even with standards, when you're creating a novel microarchitecture, especially one focused on complex ML workloads and extreme low power, you need absolute certainty. You need to know the software you compile will behave exactly as expected on the real silicon.
Makes sense.
So they use multiple tools. There's a faster behavioral simulator called MPACT-CoralNPU, good for checking functionality, early software development, runs quickly. Then there's a cycle-accurate simulator, usually based on the Verilog hardware description. Much slower, but it gives you precise clock-by-clock results, essential for the hardware team and debugging tricky timing issues.
And they use them together.
Yes. Crucially, they use co-simulation. They can run the same program on both simulators at the same time, constantly comparing the results. They use something called the RISC-V Verification Interface, RVVI, to help with this. It's like meticulously double-checking your work ensures the hardware design and the software compiler's view of the hardware are perfectly aligned.
Okay, really thorough. We've covered the architecture, the software, now the payoff.
Right.
What can you actually do with this? The target use cases seem focused on that ultra-low power ambient sensing stuff, audio processing like transcription or keyword spotting, image stuff like detecting people or gestures, general contextual awareness.
Right. Things that need to be always sensing, always processing without you noticing the battery drain.
But here's where it gets really interesting, connecting back to our show's focus, generative AI at the edge.
This is potentially the big leap forward. While the platform handles traditional ML models well, the sources explicitly state that the Coral NPU architecture is being actively optimized, working with the Google Gemma team, specifically for small transformer models.
LLMs on a 10 milliwatt chip. That sounds ambitious.
It's incredibly challenging.
Oy.
Transformers, with their attention mechanisms, are notoriously computationally intensive and power-hungry.
So how does Coral NPU even approach that?
By tuning the whole stack, they're tailoring the hardware instruction sets in the vector and matrix units and optimizing the IREE compiler pipeline to specifically recognize and accelerate the key operations found in transformers, things like sequence processing, attention calculations. They're aiming for low-latency inference on these kinds of models.
But that unlocks what, exactly?
Well, it potentially unlocks the next wave of ambient AI, truly personalized language models running locally, not in the cloud.
Yeah.
Imagine real-time, high-quality translation happening instantly in your smart glasses, powered by an LLM that's always available, always running locally. That's the kind of thing this enables.
Which brings us right back full circle to that third crisis, user trust. If you've got an LLM running locally, maybe listening all the time for translation or commands, security has to be absolutely rock solid.
It has to be foundational. And this is where they're aiming for hardware-enforced privacy. The architecture is being designed specifically to support carry. That's capability hardware-enhanced RISC-V instructions.
Jerry, what does that actually do differently than, say, good security software?
So traditional security often relies on software layers, policies, memory management units trying to keep things separate. But these can often be bypassed by clever memory-based attacks, buffer overflows, things like that.
Right.
Cherry's different. It builds security into the hardware itself, fundamentally changing how memory pointers work. It embeds permissions or capabilities directly into the pointers. Think of it like attaching unforgeable digital permissions directly to every piece of data access.
So the hardware enforces the rules.
Exactly. The AI model itself might only get a pointer, a capability that allows it to read this specific block of sensor data and write to that specific output buffer and absolutely nothing else. It creates these hardware-enforced sandboxes, isolating sensitive models and user data. It makes whole categories of common memory exploits basically impossible at the hardware level.
That sounds like a pretty significant step for securing personal data on device. Okay, finally, let's talk ecosystem. The whole point of an open standard is to solve that fragmentation tax, right?
Yeah.
To get everyone using the same tools. How are they showing this works in the real world? Is anyone actually using this?
Yeah, that's the critical validation step.
Yeah.
The sources point to a major partnership with Synaptics. Synaptics has announced their Astra SL2610 line of processors for AI-focused IoT devices. And inside those processors is something called the Torque NPU subsystem.
And Torque is?
Torque is explicitly called out as the industry's first production silicon implementation of the Google Coral NPU reference architecture.
Okay, so it's not just a research project. It's actually being manufactured by a major chip vendor.
Precisely. That's the real-world proof point. Google provides the open design, the open software stack, and partners like Synaptics build the actual chips. And crucially, the Synaptics platform also uses the same open source compiler, IRE, and the same MLIR foundation.
Why is that so important?
Because it validates the whole promise. It means developers can use this standardized IREE layer toolchain to optimize their models, and they can have high confidence that those models will run efficiently on Coral NPU-based hardware from Synaptics or potentially other vendors who adopt the standard later. It creates that shared open platform, directly reducing the fragmentation tax.
Right. So pulling this all together, Coral NPU looks like an attempt to build this foundational layer, open source, secure, highly efficient, specifically for personal on-device AI. It offers developers potentially one single validated path to get current ML models and maybe even future small transformer models running with maximum performance but using minimal power. It really feels like a platform designed for the next decade of smart wearables and ambient devices.
Absolutely. And thinking about that future, if this vision pans out, if personalized AI really does move almost entirely to the edge, running constantly on your glasses or watch, using your most sensitive data, here's maybe a final thought for you, the listener, to consider. What does integrating fundamental architectural security like Cherry really mean for personal data ownership and control? If privacy guarantees shift from software policies, which can change, to being baked into the immutable hardware design, does that fundamentally alter the power dynamic between you, the user, and the companies making these increasingly intimate devices? Something to think about as technology gets smarter, smaller, and woven ever deeper into our lives.